கண்ட்ரோலர் சார் இங்கே தான் இருக்காருங்க.
ஓகே சார்.
வி சார் வந்தோன்னா ஜாயின் பண்ணிக்குவாரு. ஓகேங்களா?
இப்போ அன்மியூட் எல்லாத்துக்கும் பண்ணுறலாம், சாருக்கு மட்டும் விட்டுறது அப்படிதானே?
எல்லாத்தையும் அன்மியூட் பண்ண சொல்லிடுங்க. உங்களுக்கும் கண்ட்ரோலர் சாரும் விசி சார் மட்டும் மியூட்ல இருக்கட்டும், அன்மியூட்ல இருக்கட்டும். மீது எல்லாத்தையும் மியூட் பண்ணிடுங்க.
ஓகேங்க.
சார் பேசுறப்ப அந்த டிஸ்டர்பன்ஸ் எல்லாம் பார்த்துக்கலாம்.
ஓகேங்க.
தேங்க்யூ.
இந்த இது ஆன் பண்ணிட்டுங்க. வாங்க. நான் மார்னிங் சூட்டிப்பாகவே இருக்க மாட்டேங்கிறீங்க. போங்கம்மா, பயங்கரமாக இருக்கணுமா? இல்லைன்னா அவனா கவுத்துட்டு போயிடுவானுங்க. அம்மா
காந்தி சார்,
சார்
நீங்க மியூட் பண்ணிக்கங்க. நீங்க பேசுறது எல்லாத்துக்கும் கேக்குது. மியூட் பண்ணிட்டு பேசிருங்க. மியூட் பண்ணுங்க. ஓகே சார், தேங்க்யூ.
Logika. Hello, good morning, Gandhi. Hello.
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 Good
Good morning, Gandhi.
morning, sir.
Tekda. Are you hearing me?
Yes, sir. Yes, sir.
He's
Gandhi,
on mute.
Hello, good morning. Are you hearing me?
Good morning, Professor Vijayaraghavan. Good morning, Professor.
Good morning, sir.
Good morning. Are you hearing?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So shortly, once the Vice Chancellor comes, we can start the program. Dr. Gandhiya Vendhan,
Professor?
are you hearing me?
Hearing, sir. Hearing.
Okay. And after Vice Chancellor visits, immediately we can start the program.
Okay, sir. அம்மா உங்களுக்கு மெசேஜ் வந்துச்சா பாருங்கண்ணா. பாருங்கண்ணா. வாங்க, பத்துங்க பத்துங்க.
बेटा बेटा हटो 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 हटो। अरे बेटा सब हटिए बेटे।
ఏది ఎలా ఛానల్ ఫోన్ మాట్లాడితే వచ్చింది ఇక్కడ అన్న కలంలో వాడినంటే అన్నకు వచ్చేస్తుంది చేతులు
சார் இப்போ கேட்குங்களா சார்?
Yes.
ஓ சார்
Yes.
ப்ரொஃபசர் ஸ்டார்ட் பண்ணுங்க. ப்ரொஃபசர் காந்தி ப்ளீஸ் ஸ்டார்ட்.
சார் ஹெச்ஓடி சார் இன்னும் பர்மிஷன் கொடுக்கலைங்க சார், அதான் வெயிட்டிங் பண்ணிட்டு.
இல்ல சீஃப் கெஸ்ட் வெயிட்டா இருக்காரு பாருங்க, வெயிட்டிங் இருக்காங்க.
இல்லைங்க சார், விசி சார் ஹெச்ஓடி சார் பர்மிஷன் வெயிட்டிங் சார்.
Very good morning to all of you. Professor Jaishankar, are you hearing me?
Yes, Professor.
Irukku sir. Okay. Shortly we are going to go for the function. While speaking, we can unmute it.
It's okay now. It's okay now.
It's okay now. Okay, okay, sir. Okay, sir. So, shall we start, sir?
Yeah.
Very good morning to all of you. Respected and honorable Vice Chancellor of Bharathiar University, distinguished speakers of today's event and tomorrow's event, the participants and my own colleagues of the department, a warm welcome to all of you on this special day. We all know that in the history of statistics and mathematics, this is one of the important day for all of us. All over the world, we are celebrating the birth centenary of the living legend, Professor C. Radhakrishna Rao. He made immense contribution to the society, not only the field as the academician, but also to the society as a human being. Numerous contributions have led the development of our own country and also at the international arena. Lots of contributions to made by him have been cited by many of the scientists all over the world, and he worked with, in the beginning, R.A. Fisher, and he is supposed to be the father of statistics, and under him he did his doctoral work, and then later he joined at the age of 28 as professor in Indian Statistical Institute, and later he moved to several other countries, and he had made immense contributions to the field of statistics. And in honor of Professor C. Radhakrishna Rao, all over the world, this day is being celebrated as a 100th birthday. Lots of dailies, particularly the magazines, like a Hindu, the Deccan Chronicle, and other magazines have given a strong words about the contributions of Professor C. Radhakrishna Rao, and in honor of him, when we approached the Honorable Vice Chancellor about a month back, he immediately said that a kind of event should be organized on this particular day. Amidst busy schedule in the campus, the Vice Chancellor has agreed to call upon all of us, and also he wanted to give the felicitation as well as the inaugural address for today's event. And I welcome Honorable Vice Chancellor for having given an opportunity for the Department of Statistics to felicitate Professor C. Radhakrishna Rao as well as organizing this kind of workshop at the international level. And this is the webinar, international webinar, and distinguished scientists have agreed upon for delivering the lectures for the two-day program. And for that, the Vice Chancellor has given a formal consent, and on behalf of the Department of Statistics, first I greet our Honorable Vice Chancellor, and also I welcome on behalf of the Department of Statistics. Of course, the distinguished speakers are there. Around eight distinguished scientists have agreed upon to give the lead lectures, and I wholeheartedly, on behalf of the Department of Statistics and being on my personal behalf, I welcome you all to this webinar. And of course, our faculty members are there, and all the faculty members have shown much interest to participate as well as to arrange this kind of event, and more than 500 participants have registered for this two-day event, and obviously all the participants should be welcomed by the department wholeheartedly, and this two-day event will definitely fetch many ideas and a new thinking for the young generation, and also the faculty who are all the seniors to the young faculty. And definitely this kind of interaction should always be there, and for the next 2 days definitely a hectic schedule will be there, and I request all of you to cooperate with us, and you make the event a grand success. And once again I welcome you all, and now I would like to call upon our Honorable Vice Chancellor to give the inaugural address, and he also admired to see the laurels achieved by Professor C. Radhakrishna Rao, and about 3 months back or 4 months back we have talked about C. Radhakrishna Rao, and he remembers the word I put with him, and today also he recalled that, and definitely the Honorable Vice Chancellor will also speak about it, because though Professor Radhakrishna Rao is not here, he is in US, and our wishes will always be there, and our Vice Chancellor will also greet him. And I welcome our Honorable Vice Chancellor to give the felicitation as well as the inaugural address. Thank you, sir.
Thank you. Good morning, everyone. respected Dr. R. Jayaraghavan, Professor and Head of Department of Statistics of our university, Dr. S. Gandhiya Vendhan, Organizing Secretary of this program, Dr. Katharina Moreira, Lecturer, Science and Engineering Faculty of Queensland University of Technology, Australia, Dr. Yogesh Shuman, Associate Professor from Indians of Science, Bangalore, faculty members and students of Bharathiar University and other academic institutions. I am thankful to Dr. Vijay to invite me for this international webinar on data science using Python in honor of the living legend, Professor C.R. Rao, centenary birthday celebrations. I'm extremely happy the scientists from India are being recognized throughout the world, and he became the faculty member at such an young age, and he still continues to give his support as well as the guidance to many faculty members and students throughout the world. Now the statistics, for the purpose of our own convenience, it was part of mathematics department several years back, about 30 years back. So it is a part of mathematics. But after that, due to the growth in the field of statistics and application of statistics, this has been separated as a separate department. Now, with the incorporation of Industries 4, Curriculum 4 and 5, there is more and more need for the contribution of statisticians. When we started the program of modifying all our syllabus, incorporating the Industries 4 component and Industries 5 component, the most important thing was the big data analytics, which is going to be useful for all the people. It is useful for the economics people, social workers, remote sensing people, biotechnology people, vaccine trial, then prediction of analysis and track control, everything. So unless we have the proper analysis of the data, it is not possible for us to be successful in our life, especially in research. So in any research work, to go from one level to another level, take for example, your vaccine trial or clinical trial. So you have to analyze the data with a minimum number of samples. And the statistician has to give the statutory warning, what will be the end result when you are going for phase 3 clinical trial or phase 2 clinical trial. If these analyses are not being made with about 30,000 samples, when you are going with a population with millions of samples, it will fail our strategy unless we analyze it properly. Today in this program, the use of Python, how it is going to be useful for the analysis of data science, and how you are going to incorporate to non-statistics department. It's more important for the statistician to make the awareness to the other departments. If they have a very good link with the statistics department, it will be easy for the scientists to bring the knowledge to the people through the best possible publications. If you are analyzing the data properly, your data will be accepted in the journal with a very high impact, factor. So it all depends on how you are manipulating your data, analyzing your data, and accumulating your data, which is going to be useful for that. So today we are having two stalwarts. One is Dr. Katharina from Australia, another is Dr. Yogesh Shuman from Indian Institute of Science. And they are going to give the impact of the use of Python and how it is going to be useful in the analysis of data science. And it is not only for the statistics department students and faculty members, even for all the faculty members, it is going to be useful. I wish the program all success. Thank you very much.
Thank you very much, Professor Honorable Vice Chancellor. Actually, we have to start the technical session with the keynote address by Katharina first and later Johanan and Professor Gandhiya Vendhan to take care of that, and you can make your presentation, and you have to tell about the focus of the program because the only with this objective we have to start the program, and the Vice Chancellor is busy with the other schedule, and later he may join with us. And now the Gandhiya Vendhan and other faculty members to coordinate the work, and first you present the focus of today's event and tomorrow's event, and after that we can go with the lecture of the lead speakers. Thank you, and it is handed over to Dr. Gandhiya Vendhan. Gandhi, you can proceed it. Gandhiya Vendhan, are you hearing? You can present
Welcome
the
to all.
focus.
Dear academic professors, most respected Honorable Vice Chancellor, Bharathiar University, and respected Professor, Registrar, Bharathiar University, Professor and the Head Department of Statistics and faculty, and welcome to all dignitaries participating of industry persons, professors, research scholars, students. Right now, the international webinar on data science using Python. The program with associate with the Living Legends Professor C.R. Rao Century Birthday Celebrations associate with the function September 10th and 11th, today and tomorrow. Right now, the program of focus, the welcome address, Dr. Katerina Maria, lecture, Decision Science, Science and Engineering faculty, Queensland University of Technology, Australia. And second keynote address, Dr. Yogesh Simgan, Associate Professor, Department of Computational and Data Science, Indian Institute of Science, Bangalore. Today evening session, Dr. Pawan Lingus, Professor and Director, Department of Computing Science, Saint Mary University, Canada. Dr. Dinesh Vishwakarma, Associate Professor, Department of Information Technology, Delhi Technology University. Dr. Professor Dibesh Gundu, Professor, Department of Mathematics and Statistics, Indian Institute of Technology, Kanpur. Mr. Venkat Vikuti Sharma, the Managing Director, Bayer USA. And the last invited speaker, Dr. Lakshman Kumar Ramasamy, IEEE Brand Ambassador and the ACM Distinguished Speaker. Thank you for all accepting my invitation. The respected all resource persons, the focusing of area data science with the associate of other relevant areas, machine learning, artificial intelligence, depends upon IIoT, IoT. Thank you, sir. Thank you for all. Now, I to call upon Dr. Jason, Professor, Department of Statistics, introduce the keynote speaker of Dr. Katerina, Professor. Thank you, sir. Thank you very much.
A very good morning to everybody. I am glad to introduce Dr. Katerina Alexandra Pinto Moreira, the speaker of this session. And currently she is working as lecturer in School of Information Systems, Queensland University of Technology. Previously, she was working as a lecturer in School of Business, University of Leicester. And before to that, she was working as a teaching assistant in University of Lisbon. During the period of her working, she got an award of excellence result in teaching award, and then Dean's Award for Excellence in Teaching in Leicester University. And the administration roles she took are the following. From June 2020 till today, she is working as an associate editor in BMC Bioinformatics, Springer Nature of Journals. And from April 2019 to till date, she is working as Deputy HDR Director in School of Information Systems, Queensland University of Technology. From March 2019 to September 2019, she is holding the post of External Research Engagement in Queensland University of Technology. And from November 2019 to till date, so she is serving as a member of Sage Athena Swan Plan Committee in Queensland University of Technology. And she was working as a PhD Deputy Director in Finance in School of Business, University of Leicester, from April 2018 to February 2019. And from November 2019 to till date, she is working as a member of QUT's Data Science Research Center. She got many awards, starting from, say, Google Grant Award from in July 2012, and then in January 2012, Best Destination Information Systems Award. In December 2014, PhD Grant Award, and she has passed her PhD with honors and distinction from the University of Lisbon, Portugal. And she has served as co-project investigator in project HEDI, how to index 1 billion high-dimensional vectors. Then from January 2011 to January 2012, she was a junior researcher in European Digital Mathematics Library project. She has given so many talks and published many research articles in reputed journals with high impact factors. The current areas of her specializations are advanced machine learning and deep learning. And now I invite Madam to present her session. Thank you.
Thank you very much for this kind introduction. So I will share my screen. Wow.
Jai Shankar.
So okay. So can you see my screen?
Yeah, ma'am.
Can you see the PowerPoints, the slides?
Yes, yes.
Okay.
Yeah, ma'am. Yeah.
Then, okay, we can all see this, right? The first slides. Okay, so my talk today will be about, like it was said, if we do not perform well data analytics and if we do not use correctly machine learning approaches in data science, then our analysis will be biased. And by being biased, we can put societal groups at risk. So my talk will be about precisely that topic. How can we make machine learning approaches more transparent and more interpretable to humans? So today I will speak to you about towards explainability in machine learning approaches, and I will also show you a Jupyter notebook approach of how to implement these approaches in Python. So let me speak a little bit about myself, although there was already a very big introduction. So again, I'm a lecturer here in Queensland University of Technology since 2019. I am originally from Portugal, and I finished my PhD 2.5 years ago. And before I was here in this role, I was working at the University of Leicester in United Kingdom. So I'm also a very passionate artist and a philosopher. I play the violin, or like my friends like to say, I do a lot of noise with the violin, but still it's my biggest companion when I travel. So this is where I come from. I come from Portugal. The two upper images is my hometown. And down you can see where I live now here in Australia. So before I can speak to you about machine learning and Python implementations and how to do this, all this data science approach in explainable, interpretable artificial intelligence, I would like first to go back and try to understand what is artificial intelligence. So it all started more or less in the 50s when John McCarthy gathered a set of reputable scientists in what it was called the Dartmouth Conference. So these four people, John McCarthy, Marvin Minsky, Claude Shannon, Ray Solomonoff, they were all the founding fathers of AI. And the goal of the conference was precisely to describe this: how can computers or computer programs solve problems that would require human intelligence or human attention. So, and they coined that this problem of a computer trying to solve these problems, they coined it artificial intelligence. So artificial intelligence is actually a very poor name for a very rich area, because we don't know what it is, intelligence, and yet we are here defining that we have some kind of artificial intelligence in our computers nowadays. So it's a very paradoxical term that they have chosen for this area, and we will understand it a little bit more throughout this talk. So the conference basically said that the goal of artificial intelligence would be to simulate the different faculties that humans have in machines. But this didn't come from the 50s in that Dartmouth conference. Actually, if we look back in history, if we try to replace machines by matter, we start to look at mythology, and we see, for instance, in Jewish mythology, we have, for instance, the golem, which is the unfinished work of God, that is also an artificial humanoid. It is made out of matter, which is clay, and it was brought to life. So even from the primordials of human civilization, there was always this tendency to put human faculties into matter. So, and this matter later developed into machines. But you see this throughout all the entire history. So Adam, for the Christians or Hebrew traditions, is also it was also made of matter. It was made out of clay as well, brought to life by God as the first humanoid, the first humankind. And perhaps here you can teach me more about this, but even in the Hindu mythology, you have the Manus. So in Hinduism, you have the different Manvantaras, and each Manvantara has a Manu, which in this case, the seventh Manvantara was Vaivasvata, the Manu, the leader of humanity that was being protected by God Vishnu here, as you can see, as the fish that he carried the people in a boat to save humanity. So there seems to be always something that is created with humanoid features. So artificial intelligence, again, it's a paradoxical term, because I need the word intelligent to actually define intelligence. No one actually knows what intelligence is. And that leads a little bit of a paradox on the field. So again, we are speaking about machine intelligence. So can machines learn? So yes, machines can learn, but learn in a different way that we humans learn. So we started with the field of artificial intelligence. It started to move towards the field of machine learning around the 80s with the development of the first perceptron. And now in 2010, we started to see more the deep learning approaches, which is nothing more than neural networks that allow us to have more hidden layers. So before we couldn't do that because of computational restrictions and because our optimization functions were not able to converge fast. So the main difference here between machine learning and deep learning is the following. So in machine learning, the user usually controls what are the features. So I have a set of input features. It goes through a classifier that decides if it's the input in this case is a bird or not a bird, and we receive the output. In deep learning, it's different because these different hidden layers, these many different layers, the more deep we can be, the more the more features the network will be able to extract. Again, it's an automatic process of extracting features. So humans no longer know what exactly is the machine or the algorithm using to classify a machine, to classify an input. So in this case, if I have a bird, it will go through a series of layers. Each layer will be extracting different features that have no interpretation for a human, and then an output is given. So, and these kinds of structures, the more deep I go into these structures, the more rich features I can extract. This allowed us to surpass humans in different tasks. So in multi-agent learning algorithms, in games, for instance, AlphaStar, AlphaGo, and so on, the machine is able to beat the human. Even in machine translation or text generation algorithms, we have now one of the biggest advancements in AI with the GTP3 algorithm. And again, Facebook also machine learning approaches. We have ways to generate new faces and so on with generative adversarial network algorithms and so on. So it's incredible how explosive this field has become since deep learning, okay? But this has problems, like I said, so like it was emphasized in the beginning or in the introductory speech of this conference, it's all about data and analyzing data. But if you do not analyze this data correctly, and yet you trust that your results are correct, you might be putting people in danger. For instance, when we are faced with deep learning systems that we cannot understand what features are being extracted, then there is the possibility that the machine learning algorithm can be reinforcing some bias in the data. Let's imagine that I'm making a facial recognition system for white people. So if you see someone from Africa, for instance, the algorithm will not be able to classify correctly, and that person might be discriminated. Again, and this of course leads to societal groups being put into danger and discrimination. For instance, job applications. If we use, nowadays people are using machines to select CVs out of different candidate applications. Well, how do we know that these machines are not already biased towards a certain race or a certain gender or a certain age group? Okay, so these are very important and serious questions. And let me show you the impact when we do not do a proper analysis. what can be put at risk. So what I'm presenting here is a predictive tool that was used in the United States of America to predict the probability of a person committing an offense or committing a crime. Okay, so we have here two people. They both have prior offenses. So we have here the person on the left that had 2 armed robberies or 1 attempted armed robbery, and the person on the right had 4 juvenile misdemeanors. So when they passed the features of these 2 people through the machine learning algorithm, what the algorithm said was that the person on the left had a very low risk of committing a crime, while the person on the right had a very high risk. But to be honest, what actually happened is the person on the left that was predicted to have a very low risk actually was the one who committed a major offense, while the person on the right did not. So in US, they are using, or they were using, machine learning approaches to try to predict the probability of you committing a crime that you haven't committed yet, and your current sentence would be based on that prediction. So this is not only unethical, it's also highly incorrect, okay? And again, you can see patterns here. You see again that different people have low risk, others have medium and high risk. And curiously enough, people with low risk were actually the ones that committed major offenses. So the conclusion of the analysis of this algorithm was that this black box or this machine learning algorithm was biased, and it was biased towards race. So as you can see here in the analysis, whenever you had an African defendant, the risk scores were nearly a uniform distribution. So it's nearly always the same. They all have the same probability of having any risk score. It's like flipping a coin. But if you go to the white defendants' risk scores, you will see that the majority of the people were categorized as having a very low risk. Risk equals 1. Okay? So you can see how biased these 2 machine learning, this black box was towards different inputs. So again, a wrong analysis or a wrong preparation of data and trusting a machine learning approach of which we do not know what features are being extracted can have serious implications when deployed to the real world. And this is not just a single case. For instance, in image classification, for instance, if it was possible to make the machine learn where was a horse in the photo, well, it seems that the algorithm had really high accuracies, almost a perfect 100% accuracy. However, when they tried to understand where were the weights or which pixels were more informative or were more used to classify this image, researchers found that it wasn't the horse, it pretty much wasn't the background, but it was something in the corner. And what they found was that since in their training set, they used images from a very famous photographer that always put his name in all the photos, then what the algorithm learned as a feature was precisely that. All photos with a horse were taken by that from that photographer, and they all had this watermark in the corner. So when they took away that watermark, the algorithm predicted that this image here was not a horse. Or in this image here, the algorithm predicted correctly that it was not a horse, but in this case, it predicted it was a horse. So as you can see, we need to be very, very careful when we use machine learning, especially for real life problems. And I could give an entire talk of 2-3 hours with just examples after examples after examples where these things are currently occurring. Another one is, for instance, in text. So this is actually a very fun paper. So it was a paper to generate analogies. And they gave lots of texts to the computer to learn from. And when the researchers ask, so man is to computer program as woman is to what? Well, the computer answered homemaker. So as you can see, the keywords that the computer is associated to a female and the keywords associated to a male, they are completely biased by the historical literature, because again, women were not allowed in many countries to write or study and so on. So of course, it was a male-dominated activity. And again, if you are still using those types of data sets for current problems, of course, the data will reflect these gender biases. So again, this asks us again the question, is machine learning enough? Then, well, that needs to come back to the word intelligence. So again, I'm a philosopher, and the word intelligence, if you go to its roots, it comes from the combination of the Latin words interlegere, which means to read in between or to choose, to pick, this capacity of discernment, to distinguish between the good and the bad, the right and the wrong. And no machine can have this discernment. Machines find patterns, but humans have the capacity of discernment. I would even dare to say that it's a pure human faculty, this intelligence in its pure sense, discernment, capacity to read in between. So in my opinion, no, machines will never be intelligent in this sense, but they will be very, very useful in things that help us to detect patterns in data. The problem is, the more complex these algorithms become, the less interpretable they are. So if we have a neural network that is highly accurate in terms of the training and test data, in terms of explainability, again, it's a black box. I don't know what features are being extracted. I don't know how this accuracy is being computed, and so on. So it seems that if one desires some interpretation or some rules that are learned, one has a trade-off in accuracy. And of course, we don't want that. Recently in Europe, a new regulation has emerged that says that companies that are based on autonomous intelligent systems, they cannot use these systems without giving the customer or the client a right to explanation. So again, it says here, the Article 22 empowers individuals with the right to demand an explanation of how artificial intelligence system made a decision. So this topic here, explainable AI, is fundamental in the days that we are at the moment, in order to avoid biases, misclassifications, and people that are put into risk or discrimination. So explainability, what does it mean? Well, in current black box approaches, I have a data set. That data set is used to train a black box. I get some predictions, and that's it. In an ideal explainable scenario approach, I would get a data. That data would go through a black box. I would get the prediction, but I would also get a justification of why. Why is the person being predicted that it has cancer? Why a person is predicted to have diabetes? And so on. So again, It will enable us to say why the system works or it doesn't work, if we can trust the results, when it's valid, how to correct an error, and so on. So we need to bring back the human into the decision-making process. And nowadays in Python, there are many ways of doing this. So again, one thing that I strongly, so this again, it's a very open research area and very recent, but something that I truly support is that if someone wants the idea that, or an explanation, that explanation needs to provide some kind of causation, some kind of saying that it was your blood pressure and your glucose levels that led to the prediction of diabetes, for instance. So again, it should not matter what the black box is. It should be communicated to the user how this prediction was computed, or at least an approximation. And Lime, and actually Python has plenty of algorithms that can allow us or help us on that. For instance, in a machine learning or a neural network that I trained for diabetes, for instance, this, for a single patient, this algorithm was able to tell me if a person, or why the black box predicted diabetes. In this case, it was because it had a very high glucose level, it was in a certain age, the body mass index plates, and so on. You also have other game theoretical inspired approaches, which is SHAP. However, their interpretability is very low for humans. It's very hard to interpret. And again, you can also use this in image data, where you can actually highlight the pixels that led to a prediction, okay? So I myself made an experiment with my students at Queensland University of Technology. And in here, what I did was I grabbed a set of faces and I put my face there in the middle. And I randomly labeled the faces as criminal and not criminal, completely random. And I trained the neural network over this. So this is an example. So I put here an image of myself, and I put also the classifier to see what the classifier would say about my picture. And the classifier said that I was a criminal. And it was funny because I showed this to the students. I showed this in social media as well. And what people replied to me was the following. They said, yes, you are a criminal because you are wearing a hoodie. You have a mean look, or you look like a criminal. So people, although this experiment that I built was completely wrong, it didn't make any sense, the students were trying to defend the black box, the algorithm, which again is very dangerous, this kind of attitudes. So again, what people need always to ask is, within a certain scenario, or a data science problem, or a data analytics problem, you need to first understand what kind of problem you are dealing with. Because if you are dealing with problems that are contextual, you need to be very careful with the approach that you are using, because machine learning is probably not the best approach. Again, if you are assessing crime like the other people in the United States, then this makes no sense, because crime is, first of all, it's independent of any facial feature, should not be even considered to be assessed by a machine learning algorithm. And again, it's contextual. What is a crime in Australia, it might not be a crime in India or in Portugal or in any other country in Europe, okay? So one should always be very critical about the scenario that... So let's see then how we can use tools and Python to help us play around with these things. So let me know if you can see... Can you see a Jupyter notebook? Can anyone speak and let me know if you can see a Jupyter notebook?
Yeah, yes.
Okay, thank you. So this, I don't know if you are aware of Jupyter notebooks, but they are a fantastic resource to do data science in Python. So you can see here, everything starts with some imports of some libraries. I just put here some helping functions. But the idea is to go very quickly to this example that I made to the students. So I basically loaded the data set with images that I converted into vectors. And again, you can see, you can even ask the algorithm. So this is one, each row represents one image where you see each pixel. And one thing that I did to trick the students was the following. They cannot see this. So, and again, it's hidden in the data set. But what I did to trick the students was the following. Whenever I had a criminal, in other words, the target that was set to 1, I always put the last 4 pixels of the photo to 0. And when it was not a criminal, I didn't touch it. So I put this, I just changed 4 pixels that are unperceived by the human eye to make students believe that we were doing a right data science approach. So you can see we have a data set of 2,000 images, more or less, with 4,000 pixels. And you can also then check or visualize these images. So Python, again, provides you the tools that help you convert this vector into, for instance, 128 by 128 image. And again, display the label that is associated to this image together with the image. And I taught the students how to learn from these structures. So again, you always start by creating, by separating the features, the pixels, from the class, from the target values of your data set. You create then, you generate then the training and test sets. Usually we reserve 30% for a test set. And we can then define a model, and we can even use Python to visualize the different layers of this model. So I'm using here a type of layer called the convolutional. But again, Python provides you lots and lots of tools to model or to train these kinds of structures. We can even plot the architecture of our neural network. So we start with an input layer, we go through a convolutional layer, we do some max pooling, dropout, and so on, until we flatten all our, so we stop extracting features. So each layer is extracting features until we flatten everything and we start to make a prediction. We can choose different optimization functions. In here, I'm using stochastic gradient descent. And I'm not going to train the model here real time because it takes a while. I already did it. But I need to compile it first. Maybe I really need to run it again because I shouldn't. Let's just go back then here. So we need to go back and run everything again so you can see the process. So again, we defined cross entropy. So let's just put it here. And we can simply start the training process where again, you see how, again, with just 10 iterations to make it fast. So again, Python provides you lots and lots of tools to help you with this. And you can see how the accuracy starts to evolve and so on. So starting from 50%, now it's on 70%. Now it's on 95%. So you see that what the layer is doing is picking up those 4 pixels that I put in the corner of the image that allows us then to detect if an image is criminal or not criminal. So 97%. And finally, the last iteration we have here. So if we were just based on accuracy, we would look at this and we would say, wow, this model is fantastic because it got 98% accuracy. And we can even plot the training curve, so no overfitting. And again, I would put an image and it would make here the prediction. It would say that I'm a criminal. Or if I put here my colleague, it would say that he's not a criminal, right? Now, again, the question is, it doesn't matter if I got very high results. It's the critical thinking is this approach correct? No, it's not, because again, although we didn't perceive it, we have here some bias. The images were manipulated to put these high accuracies. And we should be very careful with this type of analysis. And again, you can ask many types of reports in Python. So in here, it's making a couple of predictions, and now it's putting the report in terms of precision and recall. You can also see the confusion matrix, and so on. So very high accuracies. And again, as you can see, all the criminal images, if we go to the last 4 pixels, were the ones that were manipulated, while the other ones did not. So this was the reason why the algorithm performed so well. And now so this was a lecture that I give to my students, and I put them the question, what if I deployed this system? What if I said that this was a really good system to check through facial features if a person was criminal or not? Well, I could simply put in the system images like Trump or images like Putin, and the algorithm would say criminal or not criminal, with, again, completely biased, completely nonsense. You could put the image of your neighbor, and your neighbor could be discriminated by a community because of an algorithm and an analysis which was incorrect and unethical. So again, it's not about high accuracies like you see here. It's about how the experiment, how all the analysis is put together. And again, you can use these explainable mechanisms. You can, again, use these tools from Lime that would allow you to segment your image and generate explanations. So in here, as you can see, the hoodie and the part with the pixel, the 4 manipulated pixels, were being used to classify my image as a criminal. So if you like, I can later put available these notebooks so you can play around. So in here again, some kind of explainability of a black box that shows cancer and not cancer, the different features, and so on. So again, Python is a very rich tool that can allow us to make these types of analysis. It always comes down to the humans to see if they are properly correct or not. So in here in Qt, we have an explainable analytics for process intelligence group that focuses precisely on this, how to make ethical, accurate predictions in machine learning by providing the proper explanations. So we are already having our group here. If you are interested in these topics, we are accepting PhDs in our team, and so on. So to conclude, the message that I would like you to take home is, again, in the last decade, we have witnessed an impressive development of machines and algorithms with incredible predictive powers. But remember that these approaches, just because you are using an algorithm that is very trend at the moment, it doesn't mean that you are applying it correctly. You need to be always to take into consideration your business concern. What is your business question? What is the ethical boundaries here? Who would be in danger? Could your algorithm put societal groups, racial discrimination, gender discrimination, unfair job losses, and so on? So these are kinds of analysis or questions that you should make in order to assess if your analysis or your learning algorithm is biased with the patterns that it found in data or not. So, and one way to debug this is precisely by providing explainability to the machine. Put back the ultimate decision to the human. And again, the human should always have a right to explanation, understand why something happened, why the system worked, why it did not work, and when to trust the system. So that's all I had to share for today. Thank you very much. I'll be more than happy to take some questions.
Dear participants, do you have any questions? Please raise your questions.
Maybe I should stop the screen sharing.
So if there is, yeah, please.
Madam, actually, where exactly the optimization comes in that machine learning?
So it depends on the kind of algorithm. So if we have a neural networks is all about minimizing a cost function. Actually, it's not just neural networks. It's basically all the machine learning algorithms or deep learning algorithms. They all work by minimizing a cost function. And this minimization is done through different approaches. One of them can be, for instance, stochastic gradient descent. Another one can be, for instance, a DAM algorithm. That's also a very used algorithm in deep learning, and so on. So usually so in here I used stochastic gradient descent because it was a small data set. But for big data sets, I recommend something that is called ADAM, A-D-A-M. Which is a very optimized version for this minimization of the loss function.
Can we use metaheuristic algorithms for this optimization for machine learning?
Sorry?
Can we use metaheuristic algorithms? Metaheuristic algorithms like Firefly algorithm, bacterial foraging algorithms for minimizing it?
Well, there is lots of feature engineering that you can do before the training process can take place. But again, that does not save us from the process that the machine learning algorithm will always extract features that are not interpretable for humans. So in a neural network, for instance, when you go through a hidden layer, one feature is split across different nodes. So you lose the interpretation of that feature. And that hidden layer is used as input to the next hidden layer that will use again a function that aggregates all the previous layer features and so on. Less features or more important features with more quality can help improve accuracy, but still in terms of interpretability, we should always be concerned again and verify if there is some kind of bias or not in the representation of the data.
Madam, one last question. Say, for example, if you work on this cancer data set, it can be any type of cancer data set. How can we identify which particular, to mean that particular data, that is, you can able to get any number of data, right, in a cancer, that is for a particular images. For pixel wise, we can get any number of images. So how to identify which particular parameter to work on with?
So the question is, given a data set of cancer, how to choose the features, or how do I know which features were actually relevant?
Yeah, which feature extraction, which I have extracted the feature, which feature is to be very important so that I work on this particular data.
Actually, that's a very interesting question. So we have here a problem which is the following. So it is easy to extract from a machine learning approach the weights of each feature. So we call this in Python in data science the feature importance. The problem is this feature importance shows you the general mechanism of the black box. Now, let's imagine that I trained this cancer black box with 10,000 people. And it said, the black box said it was feature 1 and feature 3, the most important features, according to these weights, right? The problem of interpretability, or in this domain of explainable AI, is if I give one single patient, let's imagine myself, I want to know if I have diabetes or not. I put my local data points there. The features that are used as being the most important features of the black box usually are not the same features that are responsible for my local data point to have a certain prediction. Because one thing is how the weights represent the overall machine learning approach. The other thing is what are the most important weights that are being used for this specific patient in order to assess if he or she has cancer or not. And this is indeed an open research question. And this is exactly the core of the explainable AI. I can tell you that, for instance, in current literature, what people do is the following. Given a single data point of a patient, they do a little bit of a permutation of the features, and they pass each of these permutations through the black box. If the black box, and then from all these data that the black box classified, cancer, not cancer, well, if the person was predicted to have cancer, if you shake it a little bit, it should also say cancer. Okay, if the black box is very certain. What they do is they then fit a linear regression to these sample of data that they generated, and the weights that are used for that linear regression are the weights that are used to show the importance or the feature importance of that data point for that algorithm, for that machine learning algorithm. So again, it's a very good question, but still, when you talk about local importance, local feature importance, it's still an open research question.
Thank you, madam.
Hello, is there any other questions from the participants?
அங்க போய் வெளியே வந்து பாருங்கம்மா. ஐயாமா எண்ட் ஆஃப் செஷன்ல நான் இருக்கேன், நீங்க போய் நம்பர் வரலன்னு போகுது.
Okay, if there is no question, the Department of Statistics, Bharathiar University, wholeheartedly thank the resource person, Dr. Katrina, for the wonderful lectures on the machine learning, deep learning, and all other data science related work. So on behalf of Department of Statistics, Bharathiar University, we wholeheartedly thank once again Dr. Katrina. Thank you. Wish you all success. Thank you.
Thank you very much.
Thank you. Thank you. Now I request Professor R. Muthukrishnan to introduce the next section speaker to the participant. Now over to Dr. R. Muthukrishnan. Thank you.
Thank you, Professor Katrina, Dr. Katrina.
Thank you.
You are welcome.
Thank you, sir. So I'm audible. Anyone, please?
Yes, sir. Yes, sir. You're audible.
Yes.
Please go ahead.
Yeah. So a very warm good morning to
Yes, sir.
one and all present in this webinar. It's a great pleasure to introduce an eminent personality from an esteemed institution, the Indian Institute of Science, Bangalore, Dr. Yogesh Simhan, for this session. Dr. Yogesh holds a PhD degree in computer science from Indiana University, Bloomington, United States. Presently, he is serving as an associate professor in the Department of Computational and Data Sciences, Indian Institute of Science, Bangalore. In past, he worked as a research assistant professor at the University of Southern California, Los Angeles, and a postdoc at Microsoft Research, San Francisco. His research is mainly focuses on distributed scalable data platforms to support big data and Internet of Things applications on novel computing infrastructures such as clouds and edge services. He leads the Dream Lab, distributed research on emerging applications and machines at CDS IISc Bangalore. The Dream Lab focuses on holistic distributed systems research. He offers opportunities for research students and staff who are interested in challenging systems problems. These include design and development of novel distributed software systems, performing scalability experiments with large-scale cloud IoT systems, scaling and applying data analytics and machine learning techniques, which can lead to transformative advances to society. He has published more than 100 research articles in the reputed journals. The metrics shows that the number of citations 7,053 and H index 38 and I-10 index 81. He won the Best Paper Award, Scale Challenge Award, Distinguished Paper Award, Supercomputing HPC Storage Challenge Award in various institutions. He is serving as a member in various professional bodies, also associate editor in various journals, includes IEEE ACM. Notably, he is serving as associate editor in chief of the Journal of Parallel and Distributed Systems. Moreover, he is serving as a member Information Technology Subcommittee, Reserve Bank of India, India. Dr. Yogesh has been the recipient of number of sponsored research grants from various agencies of Government of India, which includes Ministry of Electronics and Information Technology, Ministry of Human Resource Development, Department of Science and Technology, Department of Biotechnology. He also received funding from the Indo-US Science Technology Forum. He received the research grants from NSF, National Science Foundation, DARPA, Defense Advanced Research Project Agency, and Department of Energy while at working University of Southern California. Recently, he received the Swarna Jayanti Fellowship from DST, Government of India, in the last year. It is noted that the Swarna Jayanti Fellowship are scientist-specific, not institution-specific. He is one among the 14 awardees. Even now, the COVID-19 pandemic situation, his contributions to the society from Indians of Science is a remarkable one. I would like to mention few of his thoughts and ideas into news highlights. COVID-19 from drones to testing lab. IIC offers 11 technologies. Times of India, 3rd April 2020. Indians of Science app alerts secondary contacts when someone tests positive from COVID-19. Deccan Herald, 17th April 2020. Indians of Science and the University of Southern California professors meet, discuss research and technology for COVID-19. The India Education Theory, 9th June 2020. IIC Bangalore's innovations using IoT to respond to the pandemic. The Business Economist, 28th June 2020. Such an eminent personality is here to enrich our knowledge in the field of data sciences. On behalf of the Department of Statistics, Bharathiar University, Tamil Nadu, India, I welcome Dr. Yogesh Simhan and hand over the session to Dr. Yogesh to address the gathering. Thank you, sir. Please, Dr. Yogesh Simhan.
Thank you, Mr. Muthukrishnan, for that very generous introduction. And thanks a lot for Gandhiya Vendhan for inviting me to give this talk at your symposium. It was really nice to hear the VC talk and also Professor Katrina Moira talk about some of the challenges that face machine learning, data science, from an ethics perspective, as well as some of the technical challenges that are there, as well as the opportunities that are there. So I'll sort of take a slightly broader view coming from a department that deals predominantly on data science. I just want to sort of set the context for data science as it's evolved over potentially the past decade or so. It's not something that's come up overnight. It's been a sort of gradual transition. And right now it might be a hot commodity, but it's not sort of something that arose just yesterday or day before. And people have been working broadly in the area of data science for a while. So it's useful to understand a little bit of the historical perspective as well as the opportunities that exist in data science and how as students, as faculty, as researchers, we can sort of contribute towards that. So one of the key ingredients of data science that maybe all of us have heard about is big data, right? That's been in the lingua franca for the past decade or so. And big data is, it's seemingly a sort of a marketing term that's been coined by various salespeople in the industry. But it is essentially an evolution of the ability to handle data, collect data over a period of time as it's grown. Existing technology hasn't necessarily always kept up to speed, and that sort of throws in more challenges. So about a few years back, there was back when big data, the term itself was sort of emerging, and it was people are trying to sort of make sense of that. There was a survey conducted by UC Berkeley in terms of what different people, different thought leaders around the world thought of big data, right? And based on that, they put together a wordle that you see over here. And as you can see, people have a bunch of different keywords that they think about when they talk about big data, right? It's large, it's voluminous, it's complex, there's a lot of variety, there are a bunch of techniques that are involved, a lot of processing that's involved, and so on. And just to give you an excerpt of a few of their quotes, some take it as a means by which the ability to collect data is much more easier, the ability to store it is much more cheaper. But even though you don't know what you will be going to do with the data, just collect it, keep it, and then figure out what you want to do with it down the line, because data is available right now and might as well collect it, store it, and analyze it whenever you can or whenever you have a need for it. Others think about it more from a challenging the system, data systems that are currently there, where, well, maybe 10 years back, you would have, 3 years back, you would have used relational databases. Nowadays, data is much more unstructured and much more challenging to just store it in a relational database. I'm getting an echo from someone over there, so if you can mute your mic, that would be helpful. Okay, so carrying on, so that essentially means that as data becomes more unstructured, the ability to store them and analyze them in an unstructured form also throws challenges, and that's sort of led to a lot of interest on the big data platform space and also sort of from the analytical space. And lastly, if you look at it from a data analyst perspective, again, the data is not very clean, it's not very structured. You can't just throw it in Excel or R or and sort of do your standard statistical techniques. You need to sort of define newer methods of analyzing data, and that also throws up challenges, right? So my own view of big data is sort of broadly data whose characteristics exceed the capabilities of conventional algorithm systems and techniques in order to derive value over here. So which means there are some properties of the data that cannot be handled naturally using existing algorithms, which could be things like methods and ML techniques and so on, or systems, which could be hardware and software systems, in order for you to make use of that. Right. So now let's tie in big data with the broader theme of data science. So big data is one component of data science, and data science itself takes a very interdisciplinary view of how you combine data with methods and with systems in order to make use of that, right? So, and these, the reason it's, one of the reasons it's interdisciplinary is because oftentimes the methods and techniques and systems that you apply end up being application specific, right? You can't just treat data as a black box and just say, hey, I'm just going to run all these ML algorithms on top of that. I'll get some results, I'll get some precision, accuracy, correlation coefficients, all those things, and I'll report that, I'll move on, right? As declaring success, right? So you need to actually have a much better grasp of the application domain so that you can apply the right set of techniques, you can understand the data rather than treating it as a black box, and then come up with insights and analysis that are much more meaningful rather than just being completely detached from the domain area, right? So which means that if you want to be an effective data scientist, it's not just good enough to know your ML techniques, it's also important to understand the applications where you're collecting the data and where you want to find some meaningful insights on. Right? That might actually mean that you spend some time training yourself. Right? There's a question on cancer research. It's not just about blindly saying that, hey, I have this cancer data set. I'll just sort of identify these pixels, classify them as cancer, and I'm done with that. Right? It actually means that you have to understand how imaging of cancer actually takes place so that you can sort of do more than something that's superficial. Right? The other aspect of data science is also the systems aspect, and that's sort of where my own research interests lie. And this is about how do you leverage distributed systems, how do you leverage big data platforms in order to scale the applications and the methods over large-scale data, right? And I'll actually emphasize a little bit of the big data platforms and systems down the line. And I'll also sort of motivate the need for data science based on various applications that are contemporary and that have been evolving over time as well. I won't go too much into the ML methods and AI methods. I don't claim to be an expert on that, so we just use it off the shelf. But I'll sort of maybe reiterate some of the challenges of ML that Katrina has mentioned as well, because those are very real issues that we have to deal with as data scientists, and it's good to be aware of that. All right, so what are the key sources of big data? And when you might all know that big data is all around us, right? So it's something that's been growing over time, and of the earliest sources of big data was from the World Wide Web. If you go back 20 years and you sort of think about some of the big internet giants or the big data giants like Google and so on, they came about when the World Wide Web was actually rapidly growing, and you had a need to actually analyze massive amounts of data in the public domain, right? And precursor to even that is just the number of internet-worked devices or machines around the world. So this gives you a trend over the past almost 50 years or so, since the inception of the internet, starting from a few machines all the way to over 1 billion servers or hosts that are currently or till recently were available. And as you can see, the y-axis is an exponential curve, and this has been a sort of phenomenal growth in the past 50 years or so. Something growing exponentially for 50 years is really a remarkable thing. So this is obviously plateauing out a little bit, but this is still one of the big sort of sources of big data, and one of the original sources of why you wanted to do some of these data sciences and so on. I mean, obviously, websites are the ones that are hosted on these various servers, and the number of websites themselves have been growing again dramatically. And as you can see, we have over 2 billion websites as on date. And you also see something that's interesting. This is as the web has been crawled by various search providers like Google and others. And what you'll see is that there are sort of these dips in around the 2012 and 2015 time period. It's not like the web pages disappeared. It's not like a few million web pages suddenly disappeared overnight. So this is where you actually see a tension between data for good and data for not such good things, right? So because the moment search engines became all powerful, and if you're not in the top 10 or top 20 hits in Google, you might not as well exist, right? People start gaming the system, right? They start trying to sort of do things like link farming, where you link with 10 websites and those 10 websites link with you, effectively forming a clique. And it seems to the web search engine that these are all very important sites because a lot of sites are linking to them, right? And then also a bunch of these parked websites that actually have some content pointing to existing links. So there are a bunch of these specialist techniques that are employed in order to increase your search hits. And then that's sort of then the search providers caught onto that, and then they try to account for that, right? Where they try to actually prune out these websites. So effectively, from a search engine's perspective, they're actually blacklisting some of those sites. So that's why you actually see some of these waves that take place, right? So this is an early example of where technology is not like perfect, right? So you need technology to evolve and adapt over time, and we are seeing similar issues with machine learning and data science broadly nowadays as well. The other big trend that you see is that if you look at the number of desktop and mobile users, that's sort of almost like flipping over. The last few years, we actually see more mobile users and desktop users. And what that also means is that you have, back when I was in college, right? So having a computer was a big deal, right? So 20, 25 years back, if you had a computer, you were probably the only kid in the whole block who had a computer, right? So in your home, right? Not just in school. But 20 years hence, you pretty much have everyone sort of carrying a computer that's probably 1,000 times faster than a computer from 20 years back, sitting in their pocket, and probably one at home, a laptop here, and a few cell phones there. So which means the ability to sort of perform computation or access information is growing dramatically, and it's pervasive all the time, all around you, right? It's not like you have to sit in front of a machine in order to sort of consume content or generate content, right? You could be anywhere in the world at any point in time, mostly any urban area at least, and you could sort of be a mobile user and have connectivity to the internet and so on. And again, what kinds of content do we consume or interact with? So one of the most popular one beyond the World Wide Web is obviously your social networks such as Facebook, and that again, that's sort of shown a linear trend increase over the past decade or so. And currently we have over 2.5 billion users of Facebook every month, right? Which means that almost a third or more of the worldwide population are on Facebook, and Facebook's capabilities itself has dramatically changed from just being a social network to sort of interact with your friends to everything from sharing videos, images, sort of having chat and messaging and so on. So it's become a much more sort of content that's present is much more interactive and much more engaging than its original inception. And that's partly maybe a reason why the growth has also been there. But we all know what are some of the challenges with such social networks. We are seeing these in everything from elections being tampered with using various advertising or messaging techniques to sort of social unrest being sort of propagated through sort of various chat messages and so on. So again, there are sort of two sides to the coin. So the fact that you're able to sort of interact with potentially 1 billion people around the world opens up the world for someone who might be far away from, let's say, a social structure. But at the same time, it has some challenges as well, right? And this also means that as data becomes more richer, as people start being more engaged, this data has to be analyzed not just to sort of serve content to people, but also to sort of monetize data, right? That's sort of really how the major web companies make their money, right? You're not paying a rupee to Google or a rupee to Facebook to make use of the services, right? And there is no free lunch, right? So how do Facebook and Google make money, right? And they make money by actually making use of the data that they collect about you, about your interactions, about your friends, your what you like, what you don't like, and so on. And this data is then monetized by either selling it to advertisers or for targeted campaigns and so on. So essentially, your data and your interaction patterns become a commodity that can be traded, right? And we might sort of be perfectly okay with it until it gets to a point where you start seeing that causing a change in the kind of content that's served to you or the kinds of people that you end up interacting with and so on. So those are sort of some of the challenges to deal with as well, right? But the fact that you have so much data available from these web providers means that data has to be analyzed by them. And one of the reasons why machine learning has really caught on dramatically over the last few years, things like neural networks existed for decades together, right? It's not like it was invented in the last few years. But the reason why they became popular is because they work well, the deep neural networks, if you have a lot of data, right? There's no point in throwing a deep neural network or a very sparse data and expect it to do anything. It's probably going to overfit it and it's going to be completely useless, right? But the last decade or so, given that you have Googles and the Facebooks of the world who have access to an enormous corpus of data, be it images, be it unstructured text, and so on. So you can actually train fairly complicated and robust models, and they can make seemingly accurate predictions on top of such large data sets. So in a sense, the growth and availability of big data is partly to sort of spur the whole deep learning and machine learning sort of transformation we've seen in the last few years, right? So moving on, again, it's not just sort of Facebook messages and posts. You also have sort of image data such as Instagram that's out there. And there again, it's not just analyzing text or unstructured text, it's also analyzing images and videos and so on, so that you can sort of give the right set of images when people are searching for something, or sort of show them sort of prompts for saying that, hey, maybe you like these images and so on, in terms of recommender systems. And obviously, sort of a country like India, we are big consumers of whether it's Facebook or Instagram and so on. We have a large population and we consume a lot of this content and produce a lot of this content as well. So one other interesting sort of tidbit, in case being the first time I heard this a long time back, I was definitely surprised. If you had asked me who uses the most bandwidth on the internet, right, I would not necessarily have said YouTube and Netflix, right? But that's really the reality. Between YouTube and Netflix, they actually are responsible for over a quarter of all internet traffic in the world, right? Much more so than your standard HTTP pages, right? That's barely only 7% or so. And that essentially tells you the web itself, the internet itself, is the bandwidth itself is largely dominated by maybe some of these video content and image content and so on, while the text-based data is sort of getting smaller and smaller. And that also means that it's much more easier to interpret or analyze structured text in a relational database or Excel compared to analyzing videos, right? So when you upload a video to YouTube, they have a bunch of very sophisticated algorithms running in the back end using machine learning technique, computer vision techniques to understand what's there in the images. It might actually start to be popping up the right set of advertisements for that particular video that's there, or figuring out what additional content they have to serve after you watch the video, so that you'll stay engaged in their platform, right? Or even do things like automatic transcription, right? So when you're on this Google Meet right now, I'm sure you can actually flip on some kind of sort of thing that'll turn on captions, right? And on the fly, Google is actually listening to what I'm saying and converting voice to text, right? Something like this is just unimaginable even 10 years back, right? So where on the fly, a web browser is able to run sort of very, very lightweight models and sort of translate that into text captions for you, right? So bottom line, this essentially tells you that a lot of the traffic is unstructured. There's a lot of data that's available. And all of this needs analysis, either for things like recommendations or advertisements and so on. And that's sort of been a sort of motivator for some of the advances in data science. So moving on, I just wanted to sort of, so while it might seem like big data is dominated by these large web companies and internet companies, I would argue that a lot of big data has been grounded in the scientific and engineering domain, right? Well before it became a cool term in the enterprises and the web community, right? So, in fact, one of the early sort of projects that talked about petabytes of data, right? Was about 20 years back when the Large Hadron Collider that's currently running in Europe was actually being conceived, right? They were actually planning out the Large Hadron Collider 20 years back. And back then, when grid computing was very popular and so on, they were talking about petabytes of data being collected and stored from these particle accelerators. So the idea is that you would have these huge particle accelerators, meaning 60 kilometers or so in diameter, that sort of accelerate these subatomic particles at an extremely large speed. And then essentially these particles collide with each other, and as part of that, they actually break up into much more smaller particles, which can then be observed by very fine-grained sensors that are present within this collider. And that generates terabytes and petabytes of data over a period of time, and that can be analyzed to sort of make some dramatic scientific and physics discoveries that have been sort of largely people have been trying to solve for decades together. So 20 years back, science was planning for petabytes of data when LHC came together, when even the total amount of data in the entire world was not even a petabyte, right? So that's where it's good to also look to science and scientific disciplines to see where technology might be going down the line, because enterprises are typically interested only in tomorrow and day after, and they're sort of stockholders and so on. But science has a much more longer vision. Right? Another sort of example of such large-scale data from science is this Astronomy Sky Service. There are a bunch of these around the world, pan-stars, LSST, and square kilometer array. And here, all they have is sort of these large cameras sitting at remote parts of the world. Sort of southern part of South America is Chile and so on are good examples. Hawaii is a good example, where they have these immense digital cameras pointed to the sky, and they actually keep scanning the entire sky, night sky, continuously, right? And that's because, why do you want to point your telescope at just one star or a galaxy if you can capture the entire night sky continuously on a daily basis, right? Because that way you can actually sit down in your desk later, rather than being at midnight at some remote telescope on a mountain somewhere. You can sort of let the camera do the job automatically, and then you can sit in your desk, and the next day you can actually go and actually digitally view all these the night sky of the previous night, and look at sort of the night sky for any time in the last year or few years or so, and do your scientific analysis, right? And these again generate terabytes and potentially petabytes of data. If you look at something like the square kilometer array, which is a radio telescope, it's generating petabytes of data per day, right? And just a few days back, the last LSST, they actually are in the process of upgrading their digital camera to a 3.2 gigapixel camera, and that's the most highest resolution camera that you can imagine. If you thought your smartphones had like 20 or 30 megapixel, think about 3.2 gigapixel in some of these cameras, right? So that you can imagine the size of the data that's going to be collected, right? So that's again another example of some of these scientific data sets that are being collected, and you have to actually do at large scales, and you have to do analysis on top of those so that you can advance scientific discoveries. Right? You also have things like next generation sequencers that are going to be extremely, that are already extremely useful and will become much more commonplace. And in the next decade or so, it might be fairly normal for you to go and get your sort of your gene sequenced in order to sort of help you with sort of precision medicine and so on. Right? These again generate a lot of data. Right? Just a couple of more examples before I move on. So enterprises, again, have big source, online e-commerce, we know how that trend has been happening. Fintech, again, that's been a big driver, and there you have a lot of these financial transactions, and you have to do things like detect things like fraud and make sure that you're able to scale with very low latency when you sort of want to do a UPI transaction or an IMPS transaction. The whole transaction gets done within a few seconds, right? Money goes from account A to account B within a few seconds, right? But even a few years back, right, you had to literally sort of, or maybe 10 years back, you had to literally give a paper check, and it had to be deposited, and it will take 3 or 4 days for the money to get transferred. And now you sort of take it for granted that you can do it in 5 seconds, right, rather than 5 days, right? But again, it's means that there's a lot of data about these transactions that are collected that have to be analyzed for fraud monitoring and so on, for reconciliation of accounts. That again is a lot of big data and a lot of analysis that takes place. So if you look at these are the UPI transactions, these are the ones that drive your NEFT and IMPS, IMPS based transactions in India. And you can see that it's been growing sort of exponentially in the last few years. And on the left axis, you see the amount in billions of rupees that are sort of transacted on a monthly basis. And on the right side, you see the number of transactions in millions that are transacted on a monthly basis. So we are looking at about 1 billion transactions per month more recently. And you'll see that there's a dip around here in the early part of the year, where the whole COVID situation meant that the entire country was in lockdown, so not much transactions were taking place. But you also see that as we start easing out of lockdown, the growth has been even bigger, right? Meaning that people are much more careful about not using paper currency and coins, and instead switching to online transactions, right? So, which means that things like COVID just accelerate the process of even transforming everything that we are used to doing in the physical world to doing it into the digital and the virtual world, right? Which means more data is collected, more analysis has to be done, and more products and services have to be provided on top of that, right? Likewise, the GST network is another great example of that, where a lot of transactions take place. And here again, you see a dip around April, as I think the country was in lockdown, and then you start it gradually starting to go up. Right? And lastly, the other big trend that's happening is in terms of the Internet of Things, which is sort of the next evolution of the internet, as you have not just smartphones and the servers that are connected to the internet, but even things like your a smart watch or a sort of an air conditioning unit or your refrigerator itself is going to be connected to the internet. And pretty much any consumer device or an industrial device is effectively going to become a computer that's on the network, right? And we are already looking at over 7 billion IoT devices, even as recently as 2 years back. And this growth is only sort of growing rapidly, right? So which means at some point in time, maybe it's already happened, you actually have more IoT devices compared to smartphones and servers and desktops, right, out in the world. And these are again sort of sources of data collection and actuation. So the various domains to which these IoT devices are deployed range anywhere from your buses that might have GPS sensors and cameras present on them, to sort of traffic monitoring and sort of water and power grid monitoring, to air quality and pollution monitoring. So all of these are great examples of IoT devices which are going to start being all around you as time goes on. And you might not even know that there is a sensor out there that's detecting certain ambient parameters and reporting it to some backend out there sitting in the cloud, right? But again, all this just goes on to say that data collection itself is from a diverse set of sensors. It's from a diverse set of domains. So when you want to talk about applying data science on top of data collected from these diverse domains, you need to have a little bit of idea about how the data is collected, how do you actually interpret the data, what kinds of models work for those, and so on. So it's not good enough as part of your education to be specialist in, let's say, computer science or in machine learning or sort of a specific narrow area of computing, but you have to be a generalist, right? If you want to work on data science, you can have an expertise in one area, but it's not good enough just to work with that expertise. You need to have expertise on the applications, methods, and system to sort of be a meaningful data scientist. Right? Again, this sort of alludes a little bit to what Catherine was also mentioning, right? So big data has sort of good things for society in giving access to data at the tip of your fingers, but so the transparency is much more and so on, but you also have issues of fake news that you have to deal with. So you have information, but is it good information or bad information? Is sort of still something that might be left to interpretation. You have sort of Wikipedia. It's been around for the last 20 years or so. It's been dramatic, and that's not just useful for you to sort of understand various things instead of having an encyclopedia, but also helps a lot with NLP, natural language processing. It's a great corpus of data on which, of sort of well-written data in a sense, on which you can sort of build machine learning models. And likewise, things like Twitter and sort of other kinds of social blogs have been really good for advancing democracy in various parts of the world, but they've also been used for suppressing democracy just by the lack of having access to data or internet, right? And very well in our own country as well, we've seen such issues that have been arisen, right? So at the end of the day, it's not about is data good or bad, it's the context in which you use it and context in which technology itself is used. And here again, we had several examples from Katrina. I'll just maybe add on to those, where big data or analytics has not necessarily been perfect, though you take it for granted, right? So one nice example a few years back was when we didn't have the COVID, but we had the regular flu, seasonal flu in the US, where Google said, hey, let's make use of the search trends within our sort of Google search engine to understand when people are getting the flu in the US. In the US, the flu is a seasonal thing, and it might come anywhere within a certain window within around summer or so. And getting to know when flu is going to start helps hospitals and sort of the CDC and so on have stockpiles of vaccinations distributed and so on, right? And knowing this accurately is fairly helpful when it comes to containing diseases. And Google essentially were fairly good for a couple of years, but then they sort of missed out a couple of non-seasonal outbreaks of H1N1, and they were off by a few in a certain years. And then people's trust in that started waning away, right? So even though Google might have a lot of information, really smart people building models and so on, even they can be sort of tripped up if they don't sort of use data and models accurately. And there have been a bunch of these other sort of scenarios where ML hasn't necessarily come out properly because people haven't used them with the right set of knowledge of what their shortcomings are as well. Right. So this is something I'm going to try. I don't know if the audio is going to come through. It might not. So let me know if you are able to hear this.
No voice.
Looks like, okay, they're not able to hear the voice. I'll let you sort of check it out. Look for deep fake and Mark Zuckerberg and Facebook. You should be able to pull up these videos. But even the video without the audio is going to be useful, right? So what you left is an interview that Mark Zuckerberg gave, right? Election integrity in the last US election. And just a little bit after that, people actually put together a deep fake, right? Of the video on the right is actually a completely synthetically generated video, right? And you'll be very hard pressed to figure out which is authentic and which is not, right? Meaning, of course, there are technologies that people are working towards to sort of try and detect deep fakes, but to the sort of layperson, right, to the sort of common observer, if he sees this video on Facebook or Twitter or elsewhere, you wouldn't be able to figure out if there's really Mark Zuckerberg saying something or it's someone else generating a model of him that's saying this, right? And it's one thing for Zuckerberg to say it, but it's another thing for, let's say, the leader of a country to say something like this that might be inciting violence or causing some sort of major challenges to democracy or to the citizens' rights and so on, right? So this is again an example. So the earlier example I gave was for these search engines and how some of they were trying to game it. But this is sort of the new challenge that you see where technology can potentially be put to misuse if you don't deal with it properly, right? Okay, I'm just going to move on. And again, so we've already heard about some of these biases. So I'm just going to skip past that, but that's a serious issue in the machine learning community. And likewise, it's not just, people are partly to blame as well, not just the model, because we build technology and our lack of understanding of technology can cause challenges. And lastly, you can have systems that fail as well. It's not just the methods that fail. One example from a few years back when Flipkart had their first billion-day sale, they sort of failed to provision adequate computing for all their sort of e-commerce sites, and that essentially led to a lot of outages on their website. And what was supposed to be a big day for them ended up being sort of not such a great day for people over there, right? Okay, I'm going to pivot a little bit and spend sort of the second half of this talk in talking a little bit on the systems and data platforms, right? So we talked about data science as the intersection of applications, sort of machine learning methods, and big data systems together. We had a few examples on some of the data sources for various applications. I'm not going to talk much about the ML part of it. You already had Catherine talk a little bit, and you might have other speakers talk about that as well. But I'll talk a little bit about these big data systems that help you scale some of these data science methods and applications, right? Because that's sort of close to my area of research, right? So if you think this is my high-level view of a typical life cycle of, let's say, a data analyst, right? So first you go off, acquire data from existing sources or new sources that you define. It could be sensor data, it could be web crawls, it could be various types of data that we've talked about, so on, in the public or the private domain. Then you start defining certain questions, and you start defining analytics that will help you answer those questions. It could be predictions, it could be different classifications, and so on. And then once you have your data and you have your models that work well on top of, let's say, small scale data, then you start scaling these, right? So, and that's where some of these big data platforms come in. It might work great for a small set of data on a small sort of machine, but let's say you want to scale this to 100,000 users or 1 billion users, right? So how do you do that, right? And that's where some of these platforms and systems come into play. Of course, the methods themselves, the machine learning methods themselves have to be scalable. The algorithms have to be scalable to a certain extent. But once you've taken care of that, how can software and hardware help you achieve the scalability? That's what I'm going to focus on in the next several slides, right? I'm guessing a lot of you would have come across something like this when it comes to big data. This is a very nice way to think about the different characteristics of big data. Again, this is a little bit of a marketing kind of view of things that oversimplifies things, but again, it's a sort of useful mnemonic to think about. So one, big data can have a lot of volume, which means the just sheer size in terms of number of bytes of data itself is fairly high. And we saw examples of that, potentially terabytes or petabytes of data that are going to be generated that have to be analyzed. Data could have a lot of velocity, and here these are data that typically comes from sensors or from a lot of transactions that take place continuously, be it the stock market, be it credit card transactions, be it IoT devices, and so on. And it's not just the data that the data comes in really, really fast on a cumulative basis, but it also has to be analyzed typically with low latency. If you're doing a fraud detection on a credit card, within a few seconds, you should be able to sort of either decline a transaction or accept a transaction. You can afford to say that, hey, so send me the transaction in 2 hours time, I'll let you know if the credit card was valid or not, right? Or the transaction was valid or not. And the same thing you sort of think about when you talk about autonomous vehicles, where you're actually having video cameras capture the sort of road and running models on top of that and taking decisions on terms of should you accelerate, should you brake, and so on, right? So that's another example of the high velocity data that has to be analyzed and collected in real time. You also have diversity or variety in data. Here's where the whole notion of unstructured data comes into play, where it's not just structured tables, but a lot of video data, image data, sound data, natural language, text, and so on, are all going to be unstructured. And you also have things like linked data, like your social network structure or your road structure itself is not a sort of traditional table-based data. It's much more irregular, and that itself brings about a bunch of challenges when it comes to, let's say, analyzing network data or graph data. And lastly, there's the question of veracity or trust in the data that you're collecting. Is the data itself reliable? Is that going to introduce any biases or any errors in whatever predictions that you're making, right? So these are things to keep in mind as you're designing a big data or a data science project, right? Now let's think about how do you scale your application to deal with large data and sort of make sure that you can sort of keep up with the number of users or the amount of data that you have, right? And here is sort of I'm going to dial back and look at a little bit, not too much, on the history of computing itself. And what you see over here is over the last 3 decades or so, how the computing, the CPU that you have, the computing processor that you have in your desktop or a mobile phone, how that itself has grown over time, right? And what you see is if you look at the frequencies, sometime back, and even still now to some extent, people think of the megahertz or gigahertz speed of their processor as a sort of metric of how fast your machine is, right? But what you see is that the growth of this, by the way, y-axis here is in the log scale, the growth of this has been sort of loosely matching sort of Moore's law, like Moore's hypothesis that the number of transistors will double every 3 years or so. So in a sense, the growth of the frequency was almost exponential for the initial 3 decades or so, from 75 to 2005. But at that point in time, we actually hit a physical limit. Laws of physics didn't keep up. And what you started seeing is that the energy dissipation from these processors were so high because they were running at high speeds that you actually had leakages at the level of individual circuits between electrons jumping from one wire to another wire within your CPU because the wires were so thin, microns thin, right? So that essentially led to a lot of leakage, which meant you could no longer be trusting your CPU to actually do the computing accurately, right? There might be inaccuracies, right, which is just not acceptable. So what ended up happening was that you saw plateauing out of the speed per processor, but instead what you start seeing in the bottom here in the black dots, the number of cores in a CPU started increasing, right? Which means that you have, instead of having a single processor, you started having multiple processor cores on the same chip, right? So which means that you could have, rather than having faster device, you can have more number of medium speed devices, right? And cumulatively, the number of transistors still keep increasing. So miraculously, Moore's law still holds because the cumulative number of transistors are still increasing on a single chip, though not on the single core, right? So what this means is that as of 2005, right? So if you don't know how to do parallel programming, knowing to do programming without knowing to parallel programming means that you're not really keeping up with times, right? So for the past 15 years, if you've not been learning how to use multiple processors simultaneously, you're not really an effective programmer, right? So this is an interesting opportunity, and so which means that even within a single machine, you got multiple cores. How do you effectively make use of all of them, right? That's a question. The other thing you also start noticing is that you have more and more machines available, right? If you go to a data center that Google or Microsoft or Amazon runs right now, you'll see tens of thousands of servers, right? Just aisles and aisles of servers that are just stuck together on these racks. And it's not like, meaning you do have a lot of these applications running on just a single server, but many of these challenging applications have to actually make use of many, potentially hundreds of these servers cumulatively to achieve what you want to achieve, right? Here again, so you need to sort of figure out what are the right programming models, what are the right software systems, big data platforms that can make use of these computing platforms together in order to achieve what you want to achieve, right? So that's one of the key things to remember, right? So we are no longer working in an era where we just have to think about a single thread or a single process executing. You have to think about multi-threading, multi-processing, and processing across multiple machines to perform some of these, to build meaningfully scalable systems on top of big data, right? Again, there are a bunch of reasons why cloud computing itself on these cloud data centers themselves are taken off, partly being the ease of management, because you don't have to worry about having your power and cooling and UPS and all those things sitting in your own university or your own institution. And you also get economies of scale, because when you do things in the volume business, right? So if you buy 10,000 servers, you're going to get a much bigger discount on the price of them compared to buying a single server for your own personal use, right? So the economics are also sort of cheaper. And even from an environmental perspective, to a certain extent, you can actually afford to build your data center closer to, let's say, where a sort of wind farm might be or a solar farm might be, so that you can tap into green energy that's local, as opposed to sort of pushing, let's say, coal energy to the cities, to your local data center within your university, right? So there are some potential environmental benefits as well to this. And this is what you would see if you walked into some data center. You'll actually see these rows and rows of these servers sitting on these racks. You can essentially, right now, even within a few minutes, you can just provide your credit card number and rent a virtual machine on the cloud from any of the major cloud service providers and be running on whether it's 1 VM or 10 virtual machines. You could sort of do that, right? That's sort of very enabling, right? You don't have to worry about, hey, can I afford a server that might cost 5 lakh rupees or so? If I just want to use it for 10 minutes, it might just cost you 20 rupees, right? So then that's something that you could afford, and you can sort of play around with these things without really burning a hole in your pocket, right? The other sort of big transformation that we are seeing is the growth of edge computing, right? So here, and this is partly driven by the whole Internet of Things space, where as you have more of these sensors that are being deployed all around you, you're also seeing some basic computing capabilities that are co-located with these sensors. A good example is a Raspberry Pi. It costs about $50 or so, about 3,000, 4,000 rupees for a full-fledged board. And that's a full-fledged computer. It's much faster than any computer I had when I was sort of growing up. And these can actually be used not just for collecting data and just pushing them off to the cloud, but actually doing non-trivial computing or even sort of doing inferencing of machine learning models on top of them, right? So which means that now, instead of thinking about distributed computing on many servers sitting in a single data center, you're potentially thinking about doing distributed computing across thousands of these devices that are out there on the field, right, sitting on maybe lampposts or your air conditioning units, and trying to make use of such computing capabilities for processing data, doing analysis, and so on, right? So that brings in a whole set of challenges as well as interesting opportunities. And just to sort of give you some notion of why the edge computing has non-trivial, it's to be taken seriously. It actually has non-trivial capacity. A few years back, before we ourselves sort of jumped onto the edge computing bandwagon, we really wanted to see, is it really sort of meaningful to run applications on the edge, right? And back then we were working on some smart city project where we were doing analysis over sensor data and running various queries on top of data as it came real time. So what we did was we did a benchmark of various types of queries that you see on the x-axis, where you're actually analyzing patterns within a stream of sensor data. And what you see in the y-axis is the amount of events that you can process per second, right? So higher values are better, right? These are on thousands of events per second. And the left plot is from a Raspberry Pi 2 that's about 5 years old by now. And what was then a sort of contemporary VM, a D2 VM with about 2 CPU cores. It's running on the cloud, right? And what you will see is that it's almost like a 3x kind of difference between the left plot and the right plot, right? So in terms of the trend overall. And what this essentially means is that a single Raspberry Pi CPU core has 1/3 of the CPU speed as a VM running on the cloud, right? And I'm spending about 10 cents a core on the VM on the cloud, which means that in about 3 months' time, if I'm using a VM continuously, I would have paid for my Raspberry Pi. And by the way, now I own it and I can use it for however long I want to use, right? So which means that when you're looking at a Raspberry Pi, it's not something to be sneezed at. You're literally looking at something that's maybe 1/3 of the capacity of something that's running on the cloud, a machine running on the cloud. And that sort of opens up possibilities, right? You don't have to really think of it as a tiny device. It is constrained, but not to the extent that you can sort of dismiss it away. You can start thinking of it as a full-fledged computer or a mini server on which you can start running things. Right? And some of the advantages of such edge devices like Raspberry Pi are that these are captive devices. You've paid for them. Once you've paid for them, there's no almost negligible cost until you have the lifetime of the device itself. And you also have very low latency to the data source itself. Let's say you have a video camera that's capturing videos and you want to do some basic inferencing, right, where the camera is present. You can just pop in a Raspberry Pi or maybe a NVIDIA Jetson low-end GPU board alongside the camera and actually do your inferencing, potentially even a little bit of training on top of that, without actually having to move potentially gigabytes of data from the camera to the cloud, right? So you actually save a lot in terms of bandwidth and latency for doing analysis close to the source rather than centrally accumulating them. And this starts mattering when you have a sort of lot of cameras or a lot of data that's being collected, right? On the other hand, clouds do have much larger cumulative capacity. They're much more reliable. You have sort of people supporting them and so on. But you do have potentially a higher cost if you're using it for a long term, and additional network latency and bandwidth and so on, right? So which essentially means that when you're thinking about data analytics at scale, and if you're looking at data sources themselves being highly distributed, be it a mobile phone or sort of smart city applications where the sensors are widely distributed, it makes sense to start thinking about edge computing as a primary computing platform rather than just a centralized platform like a cloud resource, right? All right, so now we talked about a bit of the computing hardware. Let's talk a little bit about the computing software that helps you make use of this computing hardware in order to process big data. And here, one of the key goals of such big data platforms such as Hadoop and Spark and many others that you might have come across is to actually make it easy for you to make use of these distributed devices, right? Be it multiple cores on a single machine, multiple CPUs on a server, or multiple servers in a data center, or potentially multiple edge devices spread across an entire city. The whole goal is to sort of how do you ease the programming of applications on top of such devices, right? And over here, the good analogy is, for example, is it easier to write assembly programming or C++, or is it easier to do C++ programming or Python, right? So, meaning obviously some of these higher level languages make it easier to program. So similarly, sort of big data platforms give you the ability to program at higher level of abstraction as opposed to doing fine-grained parallel or distributed programming. And besides easing the programmability, the other advantage of these big data platforms is also that they deal with some of the challenges that are intrinsic to these distributed platforms, and key among them being their reliability. Right? If you have a server that's highly reliable, that's great, but if you have 1,000 servers that are high reliable, the overall reliability starts going down, which means that if you're running an application over 100 servers or 1,000 servers, it's likely that, and if it's the application is going to be running for a long period of time, it's likely that one of the servers is going to fail, right? Or their hard disk is going to fail, right? So which means that failure is almost like an intrinsic characteristic of large-scale distributed systems, which means the more that your big data platform, your software platform can handle it automatically, less time that the developer has to spend in terms of dealing with it on an ad hoc basis. And lastly, we come to scalability, and this is one of the key reasons why you want to use distributed systems, right? And one thing I always tell my students, because I teach a course on scalable systems, if your application can make do in running on a single machine, right, don't get into distributed systems, right? Because I see students getting very enthusiastic and say, okay, I've got maybe 2 GB of data on which I want to run some small machine learning algorithm. Let me use Spark and ML lib on that and try to run it on 4 machines, right? That's really the wrong thing, because you spend a lot of time developing it. You're going to deal with a lot of challenges in executing it in a distributed fashion. And very likely your application is going to be running slower on 4 machines compared to running it on a single machine if you used a non-distributed system approach to it, right? So figuring out when you need to use distributed systems and when you're okay with just running it on a single machine is going to be important, right? So that's something important to know. So the key thing is, do you need scalability? Is your data going to be growing over time, or are you going to be having a larger user base across time and so on? And if so, you want to start designing your application to scale from the outset, right? But if you know that you have a captive set of people, a captive upper bound on the data, and all of it is going to fit in maybe a larger server that you can purchase or a VM you can sort of rent, then sort of stick to a sort of single machine version, right? So the key characteristic around big data platforms is something called weak scaling. And what that means is that as you increase the size of the data, right, or the number of users, if you correspondingly increase the number of processors or number of servers, your performance in terms of, let's say, the latency or time taken to complete the application is going to remain constant, right? So which means if my load increases, I just increase the number of processors and my performance remains the same, right? And big data platforms are designed to offer you weak scaling, right? So just to sort of give you a couple of examples of these before we sort of start wrapping up, because we don't have time to go drill down into some of these platforms themselves. That might have to wait for a later lecture or on your own. So the Hadoop and Spark stack have become sort of almost like a de facto in broadly the big data space. Of course, you have other kinds of platforms like TensorFlow and PyTorch and so on for specialized deep learning aspects. So I won't get into that, but this is a more general purpose. Big data platforms are sort of well served by Spark and MapReduce, where you have all these at a higher level, all these programming models where you can actually design your applications using Spark and MapReduce and things like sort of Hive for NoSQL queries and so on, that can do batch processing, that can do stream processing and searches and so on. And then you have essentially a whole set of resource management layer that sort of keeps track of distributed resources, distributed machines in the cluster, and so on. And then you have the whole storage layer. You might have distributed file systems like HDFS or a NoSQL database like HBase and so on that are storing data across distributed machines. And you might actually use things like Kafka for publish subscribe mechanisms and so on to interface across these different systems for coordination and such. Right. So if you go to sort of an enterprise or sort of one of these big web service providers, you are very likely going to see a whole stack that looks like this. Right. So again, you don't have to learn all parts of the stack. Having a big picture idea of how all these things mesh together is going to be important. But having expertise in one or a few of them is going to be helpful if you want to sort of focus on some of the scalability aspects of big data or the systems aspects of data science, right? Just to tie this in specifically with Apache Spark, what Spark gives you is a distributed programming abstraction where you can execute an application across multiple machines on top of large-scale data sets. So Spark core itself is sort of a core engine. On top of that, you have various higher-level abstractions. MLlib gives you machine learning sort of libraries that you can make use of, which are in turn built on top of Spark. GraphX allows you to do network analytics, linked data analytics. You can do lightweight SQL-like queries through SparkQL, and sort of you can do streaming data analytics using Spark streaming and so on. And the nice thing, again, maybe tying it briefly to the theme of the symposium, a lot of these things can be accessed using Python libraries or Python interfaces, right? So in that sense, Python is a really useful end-user language because you don't have to deal with some of the complexities of some of these other languages like Java and Scala. So if you want to build applications so that you can get scalability fairly easily, and you don't want to really learn too much about the internals of the system, Python is a great source. And again, things like Jupyter Notebook can easily be plugged in with Spark as well as a backend engine for you to execute. Right? All right, so I'm going to maybe use the last 10 minutes to give you an example of big data and data science at work, right? At a very high level. Again, I won't have time to go through the details. And what sort of how we've tried in the last few months at the IISc campus to try and sort of make use of some of our what we do in our research to try and address to a certain extent some of the issues around COVID, right? And these had both technological implications. These had social implications, these had ethical implications. So this is almost like a data science project in a nutshell. And it's not like we always made the right decision at all the times, but it was a very revealing thing to operationalize what we do in research and see some of the challenges that we faced as part of that. Right? As all of you know by now, we have all had a big crash course on epidemics in the last few months. So in order to manage COVID, you have sort of 4 broad pillars. So obviously, the first thing is sort of prevention using by wearing masks, socially distancing, washing your hands, and so on. And then you want to do testing just to make sure that people who have symptoms or the population at large, what's the prevalence of the virus, of the people who are tested positive. And once you identify people who are tested positive, meaning obviously they go into quarantine so that they don't spread the disease to others. But you also start doing contact tracing. And contact tracing is essentially a term that means that you want to identify all the other individuals that a COVID positive person interacted with in the past few days or week or so, right? That way you can actually identify those who are primary contacts who might have caught this infection from this COVID positive person, and then start testing them and quarantining them as well, right? That's sort of the idea behind contact tracing, right? So typically, contact tracing has historically been done manually in past part of various epidemics, which means that if someone is infected with a epidemic disease, someone does an interview with them, possibly over the phone, and asks them, hey, what all locations did you visit in the last few days, right? Or who are all the individuals that you interacted with in the last few days, right? And based on that, they actually get a history of these interactions, and then they try to reach out to those individuals to sort of see if they are having symptoms, potentially have them take a COVID test. And if they are tested positive themselves, they'll again be quarantined and so on, right? But given that this epidemic has been spreading rapidly, people have tried to use Bluetooth-based contact tracing or app-based contact tracing for accelerating the process of manual contact tracing, right? And the reasons for that are twofold. One is people don't necessarily have a good memory in terms of who all they interacted with or where all they were in the past few days or a week or so. And also, if you are in some public space, you might not even know whom you interacted with, right? You might actually be next to someone else in a bus or traveling the same bus as another person, and you would have no idea who else were there in the bus, right? So in such cases, digital contact tracing can be helpful. And the broad idea over here that's used by most contact tracing apps around the world is that these apps broadcast, these phones broadcast a unique Bluetooth identifier for that particular device, which other phones with that app that are in your vicinity can pick up, and they record that. They essentially say that at this so-and-so timestamp, I detected so-and-so device ID, Bluetooth device ID, in my neighborhood. And the nice thing about Bluetooth that sort of makes it gel well with COVID is that Bluetooth typically has a range of about 20 feet or so, 10 to 20 feet, which is sort of nicely within the envelope of how COVID spreads through, right? You need a 6 feet kind of distance. So you can sort of figure out if someone is within that 6 feet region or beyond that 6 feet region. So that potentially helps you identify people who are in your proximity, right? And by keeping a record of all these things over, let's say, the last 2 or 3 weeks, assuming a lot of people around you are actually using the app, you actually have a digital record of the other devices that were in your neighborhood in the last 2 or 3 weeks or so. And what you can then do is, let's say you keep track of your neighborhood, and if you then go ahead and if someone has tested COVID positive, then what you do is that you essentially tell them that, hey, give us a dump of all your record that you have of the people who are the device IDs that were approximate to you. And then the government might notify those particular device IDs saying that, hey, so these devices, so you are potentially in the proximity of someone with this particular, someone who was tested COVID positive. Why don't you take some precautions or go get yourself tested and so on? That's sort of the high idea of how this works. But one of the challenges with such kind of contact tracing apps, and this technique is used by both Analogies in India and various other apps around the world, including the Google and Apple's contact tracing API, the exposure notification API, is that you typically end up only doing primary contact tracing, which means that people who are immediately in your neighborhood, those can be identified since you're keeping a record of them. And it's also reactive in nature. So it's only after you're tested positive and that you actually go back and see who all came in contact with you, and then sort of try to take precautions, like not precautions, try to take reactive measures, right? So we, as a sort of pilot, we said, let's actually invert this idea a little bit, and it's not without its own set of controversies. So we essentially said, for a campus level activity, right, as an institutional deployment, let's have a contact tracing app, which we actually call Go Corona Go. You can actually take a look at it on the Google Play Store or on our website. We essentially said, let's collect anonymized contact trace data in a centralized database for that institution, right? Which means that you still collect your Bluetooth contacts in your neighborhood. These are randomized IDs. These don't identify the particular individual. These are completely anonymous, right? But let's actually upload the data to an institutional repository, right? And what that allows you to do is essentially connect all the dots together, right? So, and essentially build a proximity network, right? So what you see is the equivalent of a social network, except that it is based on the physical proximity of users to each other, right? And what you get is a graph that looks like this. So if you think of it, the contact data within each phone is almost like a adjacency list. If you go back to your graph theory or graph data structures, right? And by combining all these adjacency lists together, you effectively get the entire graph, right? And you have this kind of a global contact graph that you can build. And then what you can do is you can do not just contact tracing of your primary contacts, you can also do secondary contacts. You can get to know not just who a infected person interacted with immediately, but also who they interacted with subsequently, right? And what that means is that, let's say this particular person N was tested COVID positive, you can actually immediately find out how the risk has propagated through this entire network from N on to J, and J might have met D after that, and D might have met A after that, and C after that, and so on, which means that you can actually see the spread of the risk through the entire network almost instantaneously, the moment someone is tested COVID positive, right? And that way you can sort of quarantine not just the primary contacts, but potentially secondary and tertiary contacts as well, depending on how much of risk they've been through, right? The other thing you can also do is that you can proactively identify high-risk individuals. So for example, over here, A and D are actually form a bridge between two clusters of users on the top and the bottom, right? That means that you can actually figure out that A and D both have a higher chance of getting the virus, because they actually have a pathway to, they are in the pathway between people across the entire cluster. And they are also more prone to spreading the virus if they catch it, right? So you can actually try and sort of enhance their sort of the preventative measures that they take, or sort of test them more frequently and so on, right? So this is something that we sort of put together back in March. We started sort of evaluating them on campus. This is sort of a screenshot of the current version, version 7 that we have up and running. And the idea over here is that you sort of can keeps constantly broadcasting and scanning of its Bluetooth ID, and you can sort of it uploads it to our backend, and we also send out various updates to the users to take preventive measures, or giving them some idea of their social distancing score and so on, and also give them some sort of public knowledge on sort of the spread of the virus and so on, right? And this could very well be done in sort of a federated manner, meaning the different institutions could deploy it independently. And then you can potentially stitch together anonymous data across institutions that are physically proximate to each other, so that you can actually see how if there are interaction across people in the institutions, you can try and sort of cumulatively try and analyze that, right? So this is, let's say, the high level project, but let's see how some of the data science and big data concepts come into play over here, right? So one is you're effectively looking at a diverse set of data, right? So you have contact data that is sort of semi-structured. It's sort of networked link data that you get. You might potentially collect health surveys from different users based on the symptoms and so on. And you might optionally collect location data if they would choose to share it, GPS data from users, and across time as well. So it's a lot of structured and semi-structured data that you're collecting. And now you have to do analysis on top of that, right? So some of the analysis that we've talked about are just in terms of sheer data volume. So even if you have a few thousand users who are sending data every 15 minutes or so, that starts becoming potentially hundreds of thousands, or potentially even millions of records that are collected over time, right? So even constructing a temporal graph from all this data requires us to use platforms like Spark and so on in order to convert this adjacency list into an overall graph that can then be analyzed, right? So there's a lot of data volume that you have to cumulatively address, right? And the whole idea is that you want to design it in a scalable manner, because if this 1,000 becomes 10,000 and becomes a lakh and so on over time, you don't want to go back and re-engineer the whole thing, right? So that's in terms of data volume. You also have a certain sense of data velocity, because you're continuously getting these contact trace data on a for every 15 minutes from thousands of users. So that's potentially tens of events per second that you have to handle. And you may not need to analyze all of them in real time, right? But you may want to look at that in semi-real time. So every 5 minutes or so, you want to update your dashboard with a sense of what's the heat map for various locations on campus, so that you can understand the mobility patterns and see if some areas might be emerging hotspots and so on, right? So while the data velocity is there in terms of ingesting data, it's not necessarily a high velocity analysis that has to take place. And lastly, you do have the irregular nature of the temporal linked data itself. And there you have to sort of think about various graph algorithms, scalable graph algorithms that can scale across both time and across large topology of graphs. And here again, we use big data platforms like Giraffe for doing various types of centrality measures, such as between a centrality or degree centrality, and also look at the contact propagation, risk propagation itself, using various types of temporal breadth first search and so on. So here again, you see some of these big data platforms come to use, and sort of as you try to execute network-based epidemiological models on top of them, right? So that sort of broadly gives you a flavor as a case study, as a mini case study, right? And some of the ethical issues, again, I won't have time to go through that. I can point you to a sort of recent article we published on that. But you do have ethical issues when it comes to, even if you're collecting anonymized data, could that reveal the patterns of activity or the identity of individual inadvertently, right? So by collecting centralized data, do you run the risk of potentially giving the feel of a big brother, where you have a lot of visibility into people's activities and so on. So these are all various ethical issues that we have to deal with. We have to take a lot of care in designing the system so that it's highly anonymized, so that there's no way that data about an individual is revealed. So there are balances that there is a fine balance between the safety and health of the community at large and the privacy and rights of an individual as part of this, right? So I'll stop over here. I'll share these slides with others. There's a bunch of other reading that you can do offline. But for now, I'll stop over here, and I'm happy to take any questions if they are there.
Participant, please unmute your mic and ask your queries one by one. Please unmute your mic and ask your queries to Professor Dr. Yogesh. Please ask your queries. Or you can write it in a chat box. Or write queries in the chat box.
Hello. Good afternoon, sir. This is good afternoon, sir. This is Neha Sisodia. I'm PhD scholar working in this area. So I wanted to ask what sort of scalability issues that can be addressed. I mean, what for scalability we can contribute in this area. I'm working on Earth observation data.
Right. So Earth observation is a very interesting area when it comes to scalability, right? So one of the key challenges that many of the institutions like NASA and ISRO deal with is how do you actually, as you start getting this data, remote sensing data, how do you actually process this data? Because you're going to get continuous data from these satellite feeds. How do you actually process them? How do you actually normalize the various kinds of geospatial characteristics and so on, and make it ready for analysis, right? So way back in the past, I worked on some of these data processing pipelines, right, where you might be getting potentially gigabytes of data per day of image data that have to be resegmented and so on, right? And nowadays, with some of these machine learning models that can be applied on top of even remote sensing data, how do you actually do that at scale, right? If you have data about the entire globe or the entire low Earth observation data from India, let's say, that you're getting, can you actually define machine learning models that operate at scale to understand, let's say, various types of pollution patterns, right? So how does smog evolve across time? Or even depending on the resolution of the data, can you even detect things like mobility patterns of users so that you can understand how COVID itself might spread across a city, right, based on the density of the population and so on. But again, all of these, like I had in one of my early slides, right? Scalability is probably the last problem that you should be solving, right? From a data science perspective, the first problem is understanding what the application requires based on the data that's available and the questions that have to be answered. Next is actually defining the techniques and models that will help you answer those questions, right? And then comes the scalability problem, right? So as a scalability or a systems researcher, I actually collaborate closely with people who deal with the first two problems, right? I don't go in and say that, okay, today I'm going to start dealing with so-and-so data without having any idea about the data, right? So the best way to actually work in this interdisciplinary area is to partner up with someone who actually has a problem, who is maybe a machine learning researcher, who has a very nice technique that works on top of small data, but now they want to scale it up to a large scale data and they don't know how to do that. And that's where you as a scalability research can step in and say that, hey, I have a bunch of these big data platforms or distributed algorithms that I can put to play where I can scale your problem to large scale data sets or more number of users and so on.
Thank you, sir. So can you share your email address or the contact?
Sure, you should be able to find it on my website. Just search for my name.
Thank you so much.
It's there, yeah.
Yeah, those who want to connect to Dr. Yogesh, please see the chat box. The mail ID is circulated in the chat box. So one of the participants is asking, Shiva Pradap Singh Rajwat, is there any project ideas you can suggest related to energy analytics?
Oh, for sure, right? That's again a very interesting area, especially, I mean, that's again connected to some of this whole smart city and IoT kind of domain as well. You're seeing a lot of the energy systems, be it the large scale power grid or even within large institutions within like a campus or a software park and so on. A lot of the energy systems are highly sort of networked and have a lot of sensors present within them. And what that means is that you actually have real-time visibility into the energy consumption and the load patterns of something, everything from an AC unit or a centralized AC unit sitting within a room within an entire institution, or the energy consumption pattern of a household within urban city, right? So that's available either to the building management system or to the power grid corporation. And that essentially means that you can start at the simple level, start doing, let's say, load predictions, right? Because right now, if you look at many of the energy sort of planning within a city, because the energy power grid is a very, very sensitive system, right? If the load and the demand and supply mismatch goes beyond a certain threshold, you can actually have large scale outages, right? And things will trip and you'll have low voltage and high voltage and sort of so on. It can be disastrous. And right now, a lot of this is sort of manually sort of designed based on, let's say, the average trend across the last 1 year, right? How was 10th of September in 2019? What is the trend? I'm going to assume that the same trend is going to happen for today as well, right? But if you have real-time data coming through, then you can start doing some interesting things such as, let's say, time series analysis, right? Other kinds of predictive analysis on top of this real-time data, and help plan the supply based on the expected demand, right? And this will also help, for example, in things like renewable energy supply, right? So if you can do one of the hot areas and solve problems is, can you do predictive supply prediction on, let's say, solar energy or wind energy, right? Because the big challenge with them is that suddenly if the wind stops, right, you might have 10,000 people who are being supplied by wind energy. You can't say that, hey, sorry, the wind stopped, you're not going to get any electricity, right? So if you can actually predict some of these patterns, right, then you can actually have alternative supply that you can sort of bring online very quickly based on what if there's the load is going to be high and your supply is going to be low from these renewables, because it's, let's say it's a cloudy day and your solar panel is not going to be giving as much output. Then you can sort of bring online, let's say, some kind of a gas turbine, right, just to sort of meet those demands. So there are a lot of interesting problems with respect to both predictive models, optimization problems, as well as system problems when it comes to energy systems, both at the sort of campus scale, city scale, as well as the entire power grid scale.
Yes, sir. Yes, sir. Thank you, sir. So, in this regard, I think you have done a project while you are in the University of Southern California. You received a fund from DOE. Am I correct? DOE is Department of Energy. You have done a project related to that concept. Yes, sir.
That's
so one
correct.
more, one more question from in the chat box. The more than 1/3 of the participants are the PG students. They are asking question: how to take up research projects in data science, big data, Apache, and AI in your institution to enter into your IISc Bangalore?
Right. So there are two modes. Obviously, one mode is to come in as a student over here. If you're sort of, let's say you finish your, let's say, your master's and you want to do a PhD, or you finish your undergraduate and want to do a master's or a PhD, we do offer direct PhDs as well. You can obviously apply to IISc. If you only have an undergraduate degree, you need a GATE score along with that. But if you have a master's degree, you can directly apply for a PhD without any additional GATE score or so on, right? That's one option, right? But as a PhD, if you're already a research scholar or a PG student at your university, at Bharathiar University, and you want to sort of take up projects. So one way is to reach out to faculty, because some of us, we do offer, let's say, 6-month or 1 year kind of research internships, right? Wherein you can actually work on an existing project, right? That's going on, and you can sort of take one role or solve one part of the problem over there, right? And the way to do that would be actually to reach out to the faculty, right? But one thing you have to sort of remember is that at the end of the day, our first priority is to our own students, right? Which means that if we are bringing on board an intern, right? So you need to be able to show us that you can bring some value, right, to any ongoing project, right? So which means your existing skill set is going to be important. And that's true whether you're an undergraduate or a postgraduate or you're graduating and going elsewhere, right? Or to a company to work, right? So what are the skills that you already have, right? Because we don't expect students to come in having published 5 research papers. We don't need you to even know how to do research, right? But fundamental skills like programming, data structures, algorithms, right? Systems concepts like operating systems and so on. These are not stuff that we can teach, right? These are stuff that you should have learned as part of your undergraduate training, right? Or potentially your postgraduate training, right? So that's why to do good research, you should first be a good engineer in a sense, right? Before you can become a good researcher, right? So I still think of myself as a good engineer and secondarily as a good researcher or a scientist, right? Because you can't have one without the other, right? Especially in the computer science domain, right? So what I would suggest is, meaning having a good idea is one thing, but I would argue that making a small contribution to a big project is much more valuable than making a big contribution to a very small project, right? So think about that, right? And also think about, there are a lot of these open source projects like from Apache and others that you can always make a contribution to, right? It might, because especially at your postgraduate or your undergraduate level, research, you might have a very sort of blue sky idea of research, but sometimes research is sort of making incremental changes, but doing it in the engineering might be much more complicated, or the idea might be novel and so on. So it's very, I've been told this by my own PhD advisor, right? So your PhD is not the ultimate research that you'll be doing, right? It's the first of many steps, right? And you are not going to go and tell a baby, go and jump that big wall, right? You're going to tell it, okay, start crawling first, right? Start walking first before you can start running, right? So from your PhD or even your master's thesis and so on, have a well-defined problem, an interesting problem that has a sound definition, sound technique for solving it. And you run experiments or you have proofs and so on to show that you've solved it properly, right? So doing the entire thing, even for a small problem or a sort of small piece of a big problem, is going to be useful. And one thing I would actually, it might sound a bit wrong, but I see a lot of students who want to do socially relevant projects, right? But social relevance is not a replacement for research outcomes, right? So don't confuse the two, right? So I do socially relevant projects after I had done my PhD and I have several years of training, because I can do a meaningful socially relevant project, right? If you do a socially relevant project at your level, it might give you some satisfaction, but very few people are actually going to be using it, right? So it's purely for your own satisfaction that you're doing it rather than society's benefit, right? So instead, learn to be a good engineer, learn to be a good researcher, right? And eventually you will get the opportunity for having social impact, right? But focus on your academics and your technical skills at this point in time.
So any more questions from audience, please? Any more queries? Okay, if no queries, I will say some few words. So on behalf of Department of Statistics, I wholeheartedly thank Dr. Yogesh Siman from IIC Bangalore, India, in spite of his busy schedule. He accepted our invitation and delivered informative contents such as big data, sources of data and applications, parallel and distributed systems, and also case studies on COVID-19, entitled Data Science in Science and Society by his own research experience. Also, he answered almost all queries raised by the scholars and students and the participants. Certainly, this will help to the PG students to enter into the IIC Bangalore. Certainly, Dr. Yogesh's research ideas delivered in this webinar would help the researcher in specific data science communities to strengthen and enrich their knowledge on studying the complex problems and in turn to help the society. Once again, I thank Dr. Yogesh Siman from IIC Bangalore, India, for having given valuable inputs to data science research communities through this webinar. Thank you, Dr. Yogesh.
Thanks a lot to you and your entire team for inviting me and for listening to my talk patiently.
Thank you, sir. Further, I thank Dr. Gandhiya Vendhan, the organizing secretary of this international webinar on data science using Python, in honor of the living legend, Professor C.R. Rao, centenary birthday celebrations, for having given me this opportunity to chair this session. Thanks one and all. Now I hand over the platform to Dr. Gandhiya Vendhan, the organizing secretary of the webinar.
Thank you, Professor.
Thank you.
Now I'll call upon Dr. Satyavel, Associate Professor, Department of Statistics. Hand over the session.
Dear participants, it's immense pleasure to end the first two sessions of the first day of International Webinar on Data Science using Python. The third section is scheduled to be held at 6 p.m. today with the same Google link and YouTube, and the poster is already sent it to your WhatsApp email address. So you please join us at 6 p.m. Third session of this day one of International Webinar. The speaker of this session is Dr. Pavan Lingaras, Professor and Director, Department of Computing Science, St. Mary's University, Canada. So I request all of you join 6 p.m. sharp in this virtual event. Okay, thank you all.
Thank you, sir. Once again, thanks to most respected Honorable Vice Chancellor and keynote address, Dr. Katrina Maria, Queensland University of Technology, Australia. Keynote speaker, Dr. Yogesh Singan, Associate Professor, Department of Computational and Data Science, Indian Institute of Science, Bangalore. And chairpersons, Dr. Jayasankar, Professor, Dr. Muthukrishnan or Muthukrishnan, Professor, Department of Statistics. Once again, thanks to all professors, students, research scholars, industrial persons. Thank you to all. Thank you, sir.
Thank you, sir.
Please join the next session evening, the Google link and the YouTube link. Thanks, JP sir. Thank you, sir.